In math, we learn an operation and then we learn the operation that undoes that operation. We learn to add and then we learn to subtract. Subtraction undoes addition. We learn to multiply and then we learn to divide. Division undoes multiplication. We learn to distribute and then we learn to factor. Factoring undoes distribution. Along the same lines, we learn exponents and then we learn logarithms. We learn how to add quotients by rewriting them with a least common denominator. Up until now, we haven't learned how to undo that process. In this lesson, we will learn how to do so using a process known as partial fractions decomposition. And partial fractions decomposition is a process that undoes common denominator addition. We begin with a rational expression and decompose it into a sum or difference of a series of rational expressions known as partial fractions. That sum or difference of partial fractions is what the expression looked like before the partial fractions were rewritten with a common denominator and added together. You can always check your partial fractions decomposition by taking the partial fractions, rewriting them with a common denominator, and adding them back together to arrive back to the given rational expression. Partial fractions decomposition is sometimes known as partial fractions expansion. And we'll get into things by looking at some specific examples. Example 1, we're going to look to find the partial fractions decomposition of 5x plus 1 divided by x squared plus x minus 2. You see this is a rational expression. It's a quotient of two polynomials. We're going to see if this can be decomposed into partial fractions, which you're not always going to be able to do. So we'll look at what needs to hold true. Right, in order to perform partial fractions decomposition, first thing is that the denominator must be factorable. All right, and that's non-negotiable. If the denominator doesn't factor, then you can't do partial fractions decomposition. The second criterion is that the degree of the numerator must be strictly less than the degree of the denominator. Now, in more advanced cases, if the second doesn't hold true, then we can go through some algebra and work around that second part of things, that second criterion. In this lesson and in this course, we're only going to be looking at introductory partial fractions decomposition. So we're not going to have to get into any of those cases. We'll explore those more advanced cases next year in AP Calculus. All right, but getting back to this problem, the first thing that we need to do is we need to factor the denominator. Okay, so I'm just going to rewrite the numerator. And then look to factor the denominator. I'm going to check this factorization, x squared plus 2x minus x minus 2. Our common student mistake is to factor this incorrectly, maybe at x minus 2 times x plus 1. Right, if that's wrong, everything else in the problem is going to be wrong. So always check our factoring with distribution. That's a best practice, we'll call it. Okay, now if you wrote x minus 1 times x plus 2, everything's going to work out all right. You'll still get the same answer. Okay, so just going to rewrite that quotient, 5x plus 1 divided by x plus 2 times x minus 1. Okay, now we have to look at this and say, this is what we would have gotten had we taken simpler fractions, rewritten them in a least common denominator, and added them together. Now we're going to reverse that process. So we're going to rewrite this single quotient as a sum of partial fractions. So I know that before these quotients were added together, one of them had to have a denominator of x plus 2, and the other had to have a denominator of x minus 1. So how do you know that? All right, because in order to reverse the process, we have to understand that process. If we had these two denominators, their least common denominator would be x plus 2 times x minus 1. Now, what we're looking for in this partial fractions decomposition is what the numerators are. All right, so we have to set up expressions there to solve for. All right, x plus 2 is linear. It's first degree. So this missing numerator has to be of a degree 1 less than that. All right, if this is linear, this has to be constant, right, 0 degree, so we're going to call this a. All right, and the convention is to use capital letters always. All right, this is also linear, so this numerator has to be 0 degree. We'll call this b. All right, in this course, we're not going to deal with any quadratic or cubic factors, anything of a higher degree. We're just going to deal with simple introductory cases where we have two factors, each of which is linear. All right, so what we need to do is we need to solve for a and b. We have a rational equation right here. We're going to change its form. All right, so what we're going to do is we're going to multiply both sides by the factored denominator. So x plus 2 times x minus 1, and then multiply here by x plus 2 times x minus 1. All right. On the left, we have 5x plus 1, and on the right, after distributing, we get a times x minus 1 plus b times the quantity of x plus 2. All right, now this is in polynomial form. We're just going to leave the left-hand side, make sure it's written in standard form. Then we're going to distribute on the right, ax minus a plus bx plus 2b. All right, then we'll reorder the terms. We want the linear terms first, followed by the constant terms. All right, keep writing the left-hand side down. All right, we're going to take ax plus bx, we're going to factor in x. We want to factor it to the right, not to the left. You'll see why in a few seconds. All right, what we're doing is we're looking to match the two sides up. All right, we have 5x here and we have a plus b times x. That's why we factored the x to the right, so we can make those terms match up a little bit easier. So that tells us that a plus b has to equal 5. It also tells us that negative a plus 2b has to equal 1. Okay, and when we do that, what we've done is we've set up a system of equations that we can solve for a and b. So adding the two equations, first column adds to 0, we get 3b equals 6, which means b equals 2. And then we'll take that 2, we'll substitute into the first equation. It's a little bit easier to deal with. That tells us that a is equal to 3. All right, now we don't box these answers up. They're not the answer to the problem. All right, I got a is 3 and b is 2. If you had written these factors in a different order, x minus 1 times x plus 2, my a value would have been your b value and vice versa. All right, the partial fractions decomposition, we started with this quotient, and then we have 3 divided by x plus 2, and then 2 divided by x minus 1. Okay, that's our partial fractions decomposition. And just like we can always check our factoring with distribution, we can check our partial fractions decomposition by taking these two quotients, rewriting them in a least common denominator, and adding them back to what we started with.